I will not go through every step. As I said, it's a sketch. I'll give you the main steps in the derivation, but it gives you all the ingredients. And then if you want to see the full derivation, you can find it in many sources. One good place is to look into the textbook by Doddleson called Modern Cosmology. He has a very nice derivation there, but you can find it in other places as well. So to derive the Lensing equation, you need a full general relativistic calculation. Not very difficult, but you need to do it in general relativity because, of course, here we're looking at the trajectory of photons in curved spacetime. We saw that in the Newtonian gravity, technically the photons are not affected by, don't feel gravity because there's zero mass, but in general relativity they do. So we need to do the general relativity calculation where the curvature of spacetime or the geometry of spacetime is characterized by a metric in terms of of some general coordinates here. Okay? And of course in general relativity we've got the Einstein equation which relates the curvature of spacetime to the energy density of spacetime or the content of spacetime characterized by the stress energy tensor, and this G mu nu, the Einstein tensor, is basically can be computed from the metric through a number of steps. Okay, so that's what describes the geometry of space-time, okay, and its dynamics actually. And another ingredient that we need also from general relativity is how photons travel in this space-time, and that's given to us by the geodesic equation. So we imagine the trajectory of a photon. Let's call the coordinates of the photon x mu. We can characterize the path of this photon with some parameter lambda, an affine parameter lambda. And then we need an equation that describes the that we can solve to get the trajectory of the photon x mu of lambda. And that's given to us by the geodesic equation that tells us that photons or particles in general, but we'll be only worrying about photons here, follow a trajectory which is a solution of this equation, which is, roughly speaking, the straightest possible paths in this space-time. Okay, and the equation involves the derivative and second derivative of the position of the particle as a function of this parameter lambda. And it involves also this symbol here called the Christoffel symbol, which can be computed from the metric, as Anjan was saying, I think yesterday or day before. Okay. So this is basically a differential equation for the trajectory of the photons, and given a given space-time with a given metric, we can compute the Christoffel symbol and solve this equation, and generally get a solution for the trajectory of the photon. Now, what we're going to do is work in a specific space-time, or at least in a specific case for the space-time, where what we're going to do is look at the Friedmann-Robertson-Walker model that Anjan described, but we're going to add perturbations. And Anjan is describing all these perturbations. I think you're not doing it in general relativity. But basically, the idea is relatively simple. So if you look at this metric here, and here we're only, for simplicity, we're only going to consider flat FRW models. It could be generalized to open and close as well. But for a flat FRW model, if you ignore these terms, which include psi and phi, then you have the usual FRW model for flat space-time. So this is the flat space part of the metric, and this is the time-like part of the metric. And then here is the expansion, the scale factor A, which evolves generally on time, depends on time. Okay, and Anjan describes the solution for the evolution of A in terms of the Friedmann equation and so on. So if we ignore these two terms, this would be the usual FRW metric for an expanding universe. Okay, no problem. But what we want to consider is perturbations, of course, right? Because if the universe is completely smooth, then there's no density perturbation, so there's no lensing, so it becomes a trivial, it's not very interesting from the lensing point of view. So in general, one wants to add perturbations. And in order to do this, one needs to perturb the metric. And here we're going to go to first order only. So we had small perturbations. And it turns out that in order to do this, one needs to choose a gauge at different choices of the way we can parameterize these perturbations. We don't need to go into the details of this. But in this specific gauge, which is particularly convenient, called the Newtonian gauge, then you can write the perturbed metric like this. So it's the FRW metric plus some perturbations. There's an additional term in the time-like part of the metric, and then another term in the space-like part of the metric. Okay? And these perturbations are described by these two fields, scalar field, psi and phi, which can be thought as the gravitational potentials. Okay? And in the case where we are at late time, where we're in matter-dominated regime, at late time, which is where we are working in terms of the lensing application that we have, then actually psi and phi are related. They're equal to each other, and in this convention, they equal to each other with a minus sign. So psi is equal to minus phi. And then psi is basically the usual Newtonian potential that you get if you look at the weak field gravity limit. And this was what would correspond to the Newtonian potential in Newtonian gravity. Okay? So what we can do now is try to look at the propagation of photons in this spacetime. And in general, of course, psi and phi depend on position, right? And time, of course. And so they would correspond to perturbations in the universe. And Anjan is in the process of doing a derivation of the evolution of these perturbations in a Newtonian treatment of these perturbations. But you can also do a full general relativistic treatment and get to the same answers, so some approximations. Okay. All right, so what we need to do is consider a photon and solve this equation in a perturbed space-time like this. And in order to do this, let's look a little bit about the geometry of the lensing situation and define some quantities. Yep.
What is the motivation behind taking this metric? And why two perturbations, or like why not one? Why do we have to take the two?
Very good question. So that you can do if there was time, Anjan could give you the full relativistic derivation. But basically, the idea is the following: you can consider a general perturbation about the FRW metric. Okay, just like in GR, maybe in your GR class. Did you take GR? Yeah. There you may have looked at the full possible perturbation around the flat Minkowski metric. Okay, and there are different kind of perturbations. You can do the same thing, but instead of doing perturbation about the flat Minkowski metric, you can do it about the FRW metric. And you can write the full general perturbations, and it turns out there are different classes of perturbations. There are scalar perturbations, vector perturbations, and tensor perturbations. And that's fully general. There's no assumption there. You can classify them through their rotational property in three-dimensional space. Then it turns out that there's something called a separation theorem, which says that these different classes of perturbations evolve independently of each other. So it's very convenient. You can study the scalar perturbations on their own. You can study the vector perturbation on their own and the tensor perturbation on their own. Turns out that the vector perturbations are not very interesting because they decay with time. So even if they're excited in early universe, they decay, so they're usually not important in most models that we consider. The tensor perturbations are very interesting. They're basically the gravitational wave perturbations. But they only affect, at least to the level of approximation we're looking at here, they only affect very few observable. And in particular, they're very important for the cosmic microwave background polarization. And there's a big search for them in this using the polarization of the cosmic microwave background. But for us, they have no important effect. The most important effect for structure formation, lensing, and other large-scale structure probes are the scalar perturbations. And there you can show that without loss of generality, you can choose a gauge. And in this gauge, that's the most general scalar perturbations. So this is the most general metric, at least in that choice of gauge. The results at the end are gauge invariant, so they are independent of the gauge. So you can choose one, do your calculation that gauge, and then you get a physical result for an observable, and you could have done the same calculation on the gauge. You should get, if you've done the calculation right, exactly the same result for an observable. So there's no loss of generality in writing it like this. So that's the most general, well, not the most general. It's fully general, but there's a choice of gauge there, which has no physical significance. Where it becomes less general, but a very good approximation at late time is to let psi equal to minus phi. And then and that's a very good approximation for the cases we look at, but that's not fully general. So there's no loss of generality here. It's the most general one can write in that particular gauge. That gauge is convenient because it's called Newtonian because it can be related to the Newtonian limit of GR. So you can take the weak field limit of GR and try to connect, and you get to the Newtonian gravity, and that the advantage that this one has an explicit connection to that, and the psi becomes the gravitational potential that you have in Newtonian gravity. So it's convenient to use that one. Okay, so in order to solve the geodesic equation in this perturbed spacetime, then let's look a little bit at the geometry and introduce some conventions. So for a lensing system, we use this kind of situation. So we have an observer here, photons traveling in this direction from here to here, and then we have a source which is at some distance. Let's call the co-moving radial distance. Let's call it chi. I don't know what symbol you use, but capital R. I'm using chi here, which is the convention in Donaldson. Doesn't matter. So this is a co-moving radial co-moving radius. And then so the photons are traveling like this. They're traveling from the source, which can be thought of being in a source plane, and then at some point there's a lens, and they get deflected by the lens. Okay, so let's suppose, unfortunately you can't see it very well, but there's a line here, a brown line, which is basically the center of the coordinates, and which is centered on the source, let's say, and then let's call the position of the photon at a given moment, let's say on the source plane for the moment. So let's call it theta times chi. So theta is the transverse angle. So it's the angle. So it's the transverse angle in the transverse direction, and chi theta is the transverse displacement from the center of the coordinates, or from this line, which is from the observer to the source. And then let's suppose that we have the position of the photons. Another position of photon if we didn't have if we didn't have the lensing effect, which would be given by the position of the source times chi times theta s. Okay, and this is the one with lensing. So in lensing we would observe, so the photons would go like this. In lensing it follows a yellow. With lensing it follows a yellow path, and then chi theta is the what we would think the photons come from if we didn't have lensing. Okay, just like we saw in the previous situation from before. So then you can take the geodesic equation and apply it to this perturbed metric into this geometry, and you can derive the consequences, and after a little bit of algebra, then you find the following. Okay, oops, sorry. So if you look at the transverse part of the geodesic equation, okay, after some algebra, you can boil it down to this relation, which is basically that if you look at the transverse displacement of the photon, so how much the photon is displaced from the vertical brown line, so how much it moves, its displacement is away from this brown line, then you can show that the second derivative, which is some kind of acceleration in the transverse direction, is equal to 2 times the gradient of the potential phi. Okay, so physically it sort of means that if you have, let's say, an overdensity here, for instance, it could be the lens, then the photon feels some kind of transverse acceleration, so perpendicular to the line of sight, equals to 2 times the gradient of the potential phi. Okay, and you see this famous factor of 2, which is emerging here, which is the difference between Newtonian and general relativity. So it can be traced back to that. And so you basically imagine a photon traveling. It feels the gravitational potential generated, or the gradient of the gravitational potential generated by, let's say, an overdensity, and as a result, its trajectory is bent towards the overdensity. Okay? All right. So that's the origin of the lensing effect, basically. And then what we can do now is we can integrate this equation to derive the relationship between the position, the angular position of the photon with lensing and without lensing. And so you integrate this equation and you put the right integration constants so that the photon starts at the position of the in some position in the source plane. And what you find is that the position of the photon plus, so the position at the source is equal to the position of the photon if we didn't have lensing times a term which is basically the displacement term. And this displacement term is an integral along the line of sight distance times the gradient of the potential times some geometrical factors. And you notice that these geometrical factors is this looks like the ratio of distances that we had before, right? It looks like ratios of distances from the observer to the source, observer to the lens, and lens to the source. Okay, and that's where these factors come from. This you get by integrating the equations before. Okay, so now we're almost there. So we have looks like the lensing equation, right? It's a relationship between the position of the source, the position of the image, and related to by a displacement. And then to connect to the lensing equation as expressed, like I showed you yesterday, then all you need is one more step. You need to relate this potential to the density field, because remember in the lensing equation we're considering lens and we're characterizing by the density distribution. And that, it turns out, there's a generalized Poisson equation that you can also derive from Einstein's equation, which is basically that the Laplacian of the potential is equal to 4 pi g delta rho, where delta rho are the density perturbations. And there's also a factor of a squared, which is coming from the fact that we're now looking at a background space-time without perturbation, which is the FRW, as opposed to a Minkowski metric. So if you had Minkowski metric, this A would disappear, and you get the usual Poisson equation. But in an expanding universe, you get another factor of A squared. Okay? So you can use this relation to relate the density to the potential, and then using all the definitions that I gave you before, then you arrive at what I wrote down before, which is the displacement is given in terms of this, an integral along the transverse direction or along the plane, the transverse plane of this kappa, which remember is a rescale version of the projected density times this kernel here. And then you get your lensing equation like this. Okay? So again, I went quickly and sketched, there's a lot of sort of algebra and steps and small steps in between, but these are the main ingredients that leads us to the derivation of the lensing equation. There's no mystery. It's not that difficult. You can follow it step by step. And again, I encourage you to look, let's say, at Doddleson, Modern Cosmology, if you want to look at these steps in detail. But at least you see that it's not, there's nothing mysterious about it. Now, one thing which is convenient that will come out later is we can look at, so one way to think about this is the lensing equation is a mapping between the image plane and the source plane. So it's a mapping between the intrinsic image that we would see if there was no lensing and the one we see with lensing, right? And we saw that this mapping can be complicated. In general, it's not one-to-one. You have all sorts of effects that can happen. But locally, it's convenient to characterize this mapping by what we call the distortion matrix, which is the derivative of the source of the position in the source plane divided by the position in the image plane. So if you think of a mapping between the two, this is basically the Laplacian of that mapping. And then you can just using the equation before, you can take a derivative of this, and what you get is this distortion matrix, which we call psi ij usually, is equal to the identity metric times a term, which this is what characterizes the distortions. And this term can be written as the integral along the line of sight variable of the second derivative of the potential. And these derivatives are transverse derivatives transverse to the line of sight, or perpendicular to the line of sight, so along the plane of the sky, times these geometrical factors. And again, here you see again these geometrical factors, which are basically the angular diameter. And this is in a flat universe. So if you did it in general in an open or closed universe, you would get that these are basically the angular diameter distance from the observer to the source, observer to the lens, and the lens to the source. These are the ratios of distances that we find in the Lensing equation. And so basically what it means is that this distortion matrix, which characterizes the distortions locally, so it's the local, it's basically, if you think about it, if you look at one place in the image plane, you can do a Taylor expansion, and to lowest order you get a matrix distortion that describes the mapping locally. Then this distortion matrix can be is basically the integral along the line of sight of the second derivative of the potential times some geometrical factors. Okay, and it's convenient to write this metric, matrix, which in the following way. You can write it, of course, in general. It's a symmetric 2 by 2 matrix, so it has 3 independent quantities. So first, there's of course the identity matrix, and then these additional terms can be parameterized like this, with a trace part and then the traceless part. Okay, the traceless part is written in terms of these gammas. Here's gamma 1, gamma 2. These are called the shears. They correspond to, if you take the source plane, it corresponds to distorting, to stretching the image in one direction and flattening in the other direction. And it can be in various orientations. This is called the shear. And this one, kappa, is called the convergence, corresponds to a dilation or a shrinking of the image. And one can show that this is actually the same kappa as we discussed before, because from the Poisson equation, the trace part, you can relate it to the Laplacian of the potential, it turns out. So this is the same kappa as before. So basically this distortion matrix describes locally how the source plane is mapped to the image plane, and then so if there's no lensing at all, then you just get the identity matrix. If the image is being stretched or shrunk, this is described by kappa, and if it's stretched in anisotropically in different directions, then this is the shear. And we'll come back to that a little bit later. We'll see that one can observe some of these quantities. The one we'll be focusing on is on the shear, actually. So the shear can be observed with averaging over a large number of galaxies in the weak lensing regime. So we'll come back to that later. But the point is that if one can observe these distortions, then we can relate it directly to the derivatives of the Newtonian potential, this time integrated along the line of sight. Okay. And this is this time general. We don't have to use a thin lens approximation for this. This is true for any perturbations along the line of sight. Okay. All right. So that's the derivation, or the sketch of the derivation. So now let me go back to some examples and some applications of lensing. So first we'll look at the strong lensing application very briefly. That's not the main topic of this course, but it illustrates the physics. Also there's some important cosmological applications that are important too for cosmology. And then after that we will talk about weak lensing. So there are different applications of strong lensing, and which depends on they're sort of classified by the masses of the lens. So they can be used on various scales and various mass scales. The ones which are lensing by lenses of mass, typical masses of stars or so, is called microlensing. And microlensing has some very interesting applications. So one of the questions that happened at early time that we discussed briefly before is whether a dark matter could be made up of objects of masses like stars, okay, but would happen to be dark or too faint to be observed, to be detected. For instance, brown dwarfs or something, or very faint stars that could be baryonic, for instance, that have collapsed, but they just happen not to emit much light, and they could have been missed. So some time ago, people thought maybe the dark matter is made up of these objects, so compact objects, and they decided to search for it. Now, of course, one cannot search for it using light, because by definition they would be too dark to see. So the idea by Boden-Paczynski in 1986 is to try to use lensing to try to detect it. And what he showed is that it's very hard to do, but if we collect enough data, then one has a chance of doing it. So the idea is the following. So it's also a bit hard to see here. So let's suppose we're here. So this is the plane of the Milky Way. Okay, that's the plane of the Milky Way. That's the bulge of the Milky Way. So we're here. The sun is here, about 8 kiloparsec away from the center of the Milky Way. And then let's suppose that we look at a star, let's say in the bulge of the Milky Way. So this is the yellow dot here. Okay, so we see it, and we see the intrinsic flux of the star, no problem. And then from time to time, one of these compact objects moves close to the line of sight between the observer, the sun, and this background star. So from time to time, one of these objects moves in the line of sight, and if it's close enough, then it should produce a lensing effect. Okay? And it turns out that in that case, it can magnify the object and increase its flux, at least temporarily. Now, this is the question: how often one expects such events? I mean, this is a nice idea in principle, but how often do we expect much event? And Paczynski's calculated that if the whole halo of our galaxy, so if all the dark matter is made up of these compact objects, then one expects very few objects, but if we monitor about 10 to the 6 stars in the bulge or in the other nearby dwarf galaxies, the LMC or the Large Magellanic Cloud or the Small Magellanic Cloud, then one should expect to see enough events to detect these dark compact objects. So one needs a very large campaign to monitor a very large number of stars, and eventually we should see some events. These, by the way, this explanation for, or this class of explanation for dark matter are called, it's not a very good taste, but they're called MACHOs, massive compact halo objects. Okay? And for a long time there was this search, well, it's still continuing in some ways, but as I'll show you, the constraints are very strong. Search for these MACHOs as explanations for the dark matter. So there's a kind of a pun between the MACHOs, which are these things, and the WIMPs, which are weakly interacting massive particles, which will be more like a particle, very smooth explanation for the dark matter. Okay, so this paper by Paczynski spurred an observational effort to try to detect it and see whether one could explain the dark matter through this compact object. Now, of course, with lensing, this compact object could be made of baryons, or they could be made of anything else, any exotic matter. And lensing would be sensitive to it in exactly the same way. So somewhere it's a test of how granular the dark matter is and whether it can be explained by macroscopic objects with masses comparable to a stellar mass or so, or even less or a little bit more. Okay. Now, first, what's important is to try to see what kind of signal one do expect in these events. So one can calculate how the light curve of this background star is affected by such a microlensing event. So basically, how does the flux of this, the apparent flux of this background star changes as a function of time as a foreground object moves close to the line of sight. So this can be calculated, and this is a little animation. Okay, so the bottom shows the apparent flux of these background stars as the object moves along close to the line of sight. So, and this is again, let me show you the animation. This is time, this is the apparent flux, or the apparent ratio of the flux. So you see that early times it's equal to 1, so it's equal to the intrinsic flux, and then as the object moves close, then you get this amplification and it goes back down. And it turns out that this curve is very generic to this lensing event and has a very specific profile that one can look for. What is shown above is the position. So this is the position of the lens. So we move we go in a frame where the lens is at rest, and then we move the star relatively to it. Of course, in practice, it's the other way around. And what is shown, if I can show it again, is the two images that one sees. So this is the red is the position of the source if it were not lens. So this is the position of the source with respect to the lens. Okay. That's the Einstein radius of the lens. And then in blue, it's the two images. Remember, we get two images for a point like mass. So we get one image here, another image here. Oops, let me try again. And you see that we get these two images, and you can add the fluxes of the two images. So this will be the fluxes of the two images together, and you get this curve. It turns out that in microlensing, the stars are not resolved, so they're very small. They're not resolved, so we cannot resolve the two images. We have all we can see is an average flux over the entire surface. So the only thing that one can see is the total flux of the image. We cannot see and resolve these two images. So the idea is to monitor a very large number of stars and try to look for events like this. Okay? And of course, it's difficult, not only because we need to monitor a very large number of stars, but also because there are a lot of other objects. Stars are actually, many of them are also variable. So you have variable stars which vary for completely different reasons, from astrophysical reasons, small variations in their luminosity, in their fluxes. Sometimes actually it's quite large variations. So one needs to remove these background events, which is not what people are looking for, and search for these very specific events. Now, amazingly, people could. It works. So people found some events. So this is an example. In this model, they're point mass also. They're not resolved. So they're not point mass. So they would be the size of a star, let's say. But for the resolution of that experiment, they act as a point lens. That's right. But they're not thought to be a point, of course. They're thought to have a finite extent, but it's so small that it has no impact on the lensing profile, on the light curve. That's right. Okay, so people have found it. This is from one of the experiments. There are several experiments that look for these events. This is called the Ogle experiment, and you see several events here. The one in green, the data points are in blue. The one in red, the data points are in black. This is the curves are the fit using these microlensing light curves that we expect, and this is the residual. So you get very good fits. And now there are a very large number of events that's been detected. So the question is whether the number of events that one sees is compatible with having the halo filled with stellar mass-like objects, and the conclusion was no. There was not enough events to explain it. There was enough events to be consistent with a known stellar population, because of course it could have a regular star that one can detect, produce also a microlensing effect, and in fact that's what a lot of people see. They also discovered some very interesting things about the structure of the galaxies and the distribution of stars in the galaxy, but the number of events that they saw was not sufficient to explain the dark matter of the halo. So that led to the conclusion that dark matter is most likely not made up of these machos, basically. And that's where the constraint on the granularity comes from. And therefore, now our preferred model are a smooth distribution of halos, of dark matter in the form of particles. Now, as somebody said, There's still a little bit of parameter space in the mass of this compact object which is left, and some people are continue exploring this, but this is no longer the favored model. So now people think they're weakly interacting massive particles. So of course this was a very important constraint on cosmology, because it gave us a clue about what dark matter is made up of. Now, amazingly, one can push this measurement a bit further. Now we're going beyond cosmology, but it's, I think, so interesting I wanted to mention. So what if you have a star? So let's go back here. Let's go back to a situation that you can barely see. But let's suppose that, so we are observing here, we have a background star that we're monitoring, and then there's another star that moves towards close to the line of sight, producing a microlensing event. But let's suppose that this star had a planet around it, orbiting around it, the lens. So the lens, okay, which is producing the microlensing event, also has a planet. Okay? Could the planet has an effect on this microlensing? Can we detect it in microlensing? And amazingly, yes. Okay? And people have detected planets around stars using microlensing. Okay? This is an example, one of the first detection in 2006. So you see here the light curve of the star. This is a usual microlensing event from the star lensing another star. Okay, and it has a very nice shape. You see now it's measured extremely well. But you see there's a little blip here, and if you zoom on the blip, you get this. And this is actually the planet orbiting around the star. So if the geometry is right, you can actually detect planets like this. And this is a very important application, because using this, you can actually statistically count the number of planets around stars. And it turns out that this is actually very sensitive to planets which are, at least potentially with better experiments, to planets that are the mass of Earth, or close to the mass of Earth, as the typical distance between Earth and the Sun. So planets which potentially could harbor life. And this technique is very sensitive to such planets. There are many techniques to search for extrasolar planets. As you know, it's a very active field as well. And this is one which allows, at least statistically, to count the number of such planets in a very interesting regime of potentially habitable planets. That's ongoing. Now, amazingly, with this future experiment, what can go even further? Because what happens if the planet has a moon around it? I mean, it sounds crazy, but you have the star, planet around it, and then the planet with moon. It turns out that these future planned experiments could be also sensitive to moons. So you would have a tertiary event here along the planetary event. So it shows you how amazing these measurements are. So there's a lot of work and very exciting work to be done on this in this regime of lensing. And again, it's a way of searching for things that doesn't emit enough light to see it. We could not see the moon of a planet in an extrasolar system, but through its gravitational effect, if the geometry is right, statistically from time to time we can see them.
So would it like one planet corresponds to one such?
Yes. So the planet, when it's oriented in the right way, corresponds to this little blip here. Yeah, you get different blips. Again, if the geometry is right, you can get potentially different blips. You can also do binary stars. So if the two stars are orbiting around each other, then you get more complicated light curve. You can also characterize the binary system like this.
So they also contribute in lensing, no?
The planets.
Planets.
Yes, that's right. That's what's causing this little blip here. On their own, they wouldn't be massive enough to have a detectable event, but the light is already very amplified by the star itself, and this is a perturbation around the star. And because lensing in this regime, strong lensing, is non-linear, then you can actually detect it through the combined lensing effect of the star and the planet, or even the moon.
So is there any lower limit on the mass of star for this microlensing?
Yes, at the lower limit, I don't know what it is, but it's less than a solar mass, but I don't know exactly where it is, but there's a lower limit. Yeah, there's also an upper limit, which I think is around 10 solar masses or slightly more or something. So there's a range of masses which are ruled out, basically, in terms of their contribution to the dark matter in the halo, but they're still extreme above and below these maximum minimum. Then there's still a little bit of space for explanation of dark matter with machos. Yeah, it's not sensitive to all range of masses, right? But it's a relative broad range that it can probe. All right, so now let's go back to larger scales and more cosmological scales. We can also have lensing done by galaxies or clusters of galaxies. Okay, so here are examples. So these are strong lensing. Unfortunately, it's a bit bright. It's hard to see, but we'll give you the slides. You can look at it on your screens. So these are examples of strong lenses by galaxies. So here the lens is a galaxy, and in the background, what is lens is either a galaxy or a quasar. So here you see nearly Einstein ring. Okay, so the center here would be the lens, the galaxy, which is a lens, which is lensing in this case. You also see its light profile, so here you can detect it. And you see a ring here. Here, I don't know if you can see in the back, but here is another galaxy, which is a lens, and you see these arcs here, which are background galaxies stretched by the lensing, whose image is stretched by the lensing effect. Here is another one with several images. You see, you have 1, 2, 3, 4. It's probably a background quasar or background galaxy, which is multiply imaged by this lensing galaxy here. Here, I'm not sure you can see it. There's also several arcs here, maybe multiply imaged. Here, there's an arc. So again, I encourage you to look. You can look at it on my screen afterwards if you want. And here, another one here. Okay, and there's now, so this is all Hubble Space Telescope images, and there's now a very large number of known lenses. And you see that it's very hard to imagine that objects would actually have this kind of configuration without lensing effect. And you can confirm spectroscopically. In many cases, one can take a spectra of these different images, and they're identical. One can also look at the time curve. So some of these, for instance, quasars are time variable. So you can look at the time curve of each of these images. As I was telling some of you yesterday during the break, amazingly, there's also a delay between the photons arriving from the different lenses, because the light paths are slightly different. The delays can be quite large, can be weeks, can be months, and so on. And so by monitoring, if you monitor these different images, I don't know if it's the case in this one, but if you monitor some of these, the different images in some of these systems, you can make a light curve for each of the image, and you see that they're very close to each other, almost identical, but with a delay. And you can measure that delay, and you can use that delay to characterize further the lens. And also it turns out that can be used to measure the Hubble constant. So it turns out the Hubble constant comes into the delay, and that's one powerful techniques for measuring the Hubble constant, by monitoring these time delays in these systems. Now it takes a long time because you need a very long baseline, like typically many years, in order to measure the time delay properly. There's also noise in the system, in the measurement. It turns out there's also microlensing, which causes a problem because there's also stars inside the lens galaxy that are moving around, and that tends to produce amplification and de-amplification of some of the images and not the others. So that adds noise and perturbations to the light curve, actually. Very interesting phenomena, but that needs to be also modeled and removed from the measurement. So there's a large number of people doing these kind of measurements to both constrain the lens better and measure the halo distribution, the dark matter halo distribution of the lens, and also to do a cosmological measurement like the Hubble constant. These are other systems with near Einstein rings. So you see they're very impressive. So here you have multiple images with almost a ring here, same thing. So again, the lens is the yellow and the image, the lens image is in blue. Another one here, 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 almost like a ring here, here, almost like a ring here. And this is an example, a very clear example of a multiple image lensing system. So this is the lens, but these are 4 images of the same quasar, I think, in this case. Okay, very clear quadruple images in this case. So as I said, if the lens is spherical, you only expect 2 images, but if the lens is not spherical and is elliptical or more complicated, then you can have more than 2. In this case, it's 4. Yeah, so yeah, that's part of the difficulty in these measurements. So you need to model. Well, first you can look at the spectrum, which may not be the same. So if it's a quasar in one case and a galaxy in the other, and the redshift is different, so they're redshifted, so you can use the spectrum to distinguish, the color if you wish, to distinguish. But otherwise you have to model the light distribution of the lens. We have a very good idea of how the light profile of galaxies are, so they fall under to a good approximation in some specific manner, laws, so you can use that. You typically model it, fit it, and model it, and then you're left to modeling the lens, the images. But that's part of the difficulty and the trick here. That's a good point. All right, now moving to larger scales, we can now, instead of considering galaxies as lenses, we can look at the larger structures called clusters of galaxies, which are the largest bound structures in the universe. So they are systems of typically 1,000 galaxies. They have about 10 to the 14 or 10 to the 15 solar masses or so. So they're basically the largest lenses that we have available. And lensing has been discovered in clusters also, and now there's a lot of systems where it's seen. So this is an example, again with Hubble Space Telescope observations. So the yellow galaxies are member galaxies of the cluster, so they're in the foreground and they act as the part of the cluster that acts as a lens. Of course, there's dark matter also distributed along with them. And then all these arcs of different colors, and if you come to my screen, you see there are many of them. It's actually amazing how many there are basically background galaxies whose images have been distorted by the lensing effect. And you see they fall kind of in kind of a ring. Now the size of this ring corresponds to the Einstein radius, but because the background galaxies can be at different redshifts, remember in the Einstein radius, to compute it, there's a dependence on the redshift of the distance to the background source. So if the background source is at different redshift, if you have several, then the Einstein radius is different. So that's why they're not all on the same circle, basically. And also the potential here is complicated, and so it's not quite spherical, and there are many other effects. You also see, for instance, a subclump here with 2 galaxies, and you see arcs around it. In fact, when you look closely, there are kind of arcs everywhere. And all of these, and you see some thin ones here, some here, all of this. Okay? So one can model all these arcs together and map and get constrained on the gravitational potential of this cluster. And that way we can weigh the mass of clusters, which, as I said, is one cosmological probe. Counting the number of clusters as a function of mass has a strong dependence on cosmological parameters, so one can do this. That's another example. This one is kind of fascinating. So this is another cluster. So the yellow galaxies are members of the lens cluster, and then the blue sort of structures here are images of multiple images of a galaxy. And here with Hubble Space Telescope, the resolution is so good that one can see structures in that lens galaxy, right? And you can recognize some of the same structure. Okay, you can resolve the structure of the background galaxy in this case. And one can do, people doing this, Collet et al., what they did is they reconstructed the source. So they reconstructed the shape of the source before it was lensed by inverting the lensing equation. And basically, they got kind of a pretzel shape. So they call it the pretzel galaxy. So you see that it has a pretzel shape, and it gets distorted very strongly into these arcs. Okay, and here it's obviously the same galaxy, because not only has the same spectrum and so on, but it has this recognizable shape.
What I feel that if you have only 2 objects, means one original object and one is lens, then it is clear that you can have multiple images or two images or you can have Einstein ring.
Mm-hmm.
Okay, but because in universe we have so many objects, and so it will happen like this, no, that the lensing effect of these objects may get distorted, and means the object which is behind this, behind that galaxy or star, that image will also come, no? That confusion would not be there.
Yeah, so you have to be careful that you identify these multiple images correctly. That you don't say that this is another image of the same object, but it could be another galaxy which has nothing to do with it, right? So that's what I was saying. For that, you can use spectroscopy. You can look at the spectrum of these galaxies, right? And if they're identical, that's a very strong hint that they're coming from the same object. And you can, in this case, which is quite remarkable, it's not always the case, but you can also look at the morphology, so the shape of the images, which in this case are very similar, and so gives you another very strong hint that they're images of the same galaxy. So they have the same spectrum and the same shape. So that's a very strong indication. But from time to time, there will be confusion and errors and so on. So you have to just be very careful in your identification, and it introduces errors, and that's part of the difficulty. Yeah. Okay. So the cosmological applications of strong lensing by galaxies and clusters of galaxies are manifold, so there are many of them. As I said, one is we can measure the mass of galaxies and clusters of galaxies. For clusters in particular, that's a very interesting cosmological probe. By counting the number of clusters as a function of mass, one can get strong constraints on cosmology. The difficulty is to get the mass. There are many techniques to measure the mass of clusters, but lensing is one of them, and is a powerful way of doing it. We can also measure the mass profile, so not only the total mass, but how the mass behaves. We can even make a map of the mass and compare to theories of structure formation. We can do astrophysics. We can compare the distribution of baryons, the distribution of the dark matter, see whether the dynamics make sense, and learn about the physics of the baryons and how they collapse. So compare with theory of structure formation. And then another application, which is more for astrophysics, is to use the lenses as gravitational telescopes. Because after all, as I told you, in some of these systems, the flux of the background source has been heavily magnified. And the magnification can be by very large factors, of 10 or more. So the idea that some people are following is to use the gravitational lensing systems, like a cluster of galaxy, as a gravitational telescope to allow us to see objects which are too faint or too far to have been seen otherwise. So people use this magnification effect of lensing to detect very distant objects, and so people map the regions where there's strong lensing amplifications and look for very faint objects and try to detect higher redshift galaxies, higher redshift quasars, or very faint objects. And so people do this as well. Okay, so maybe I'll start. I was just going to start on weak lensing proper, so maybe I can start slowly and give us the principle. So now let's move to weak lensing. So as you saw here, in the case of a cluster of galaxies, we have some region where the distortion is very strong, okay, and that's what we call strong lensing. But if you look at galaxies which are far from the center of the cluster, then the distortions, the lensing distortions, are much smaller. In fact, sometimes you can't even see them by eye, but they can still be there, and as I'll show you, we can statistically detect it and map the dark matter or the mass even in regions where the lensing is weak, okay? And that's what we call weak lensing, and that has very important cosmological applications. So first, let me tell you about the theory or the principles of weak lensing. The physics is completely described by the lensing equation described before, but let me illustrate it with a few diagrams to make it more explicit. So let's suppose that we have an observer here and background objects here. Background object, let's say a distant galaxy, all right? So as we said before, in the absence of structures along the line of sight, then the light would travel in a straight path. We're ignoring the expansion of the universe and so on for the moment, just for simplicity. And so we would see the intrinsic shape of the object. Okay. Now, if we have structures along the line of sight, let's say galaxy clusters or galaxy overdensities, doesn't matter what it is, then the light path gets affected and the photons travel in a curved trajectory. All right? And so as a result, instead of seeing the intrinsic shape of the object, we see a distorted version of the object. And if the lensing is weak, it's a weak distortion. All right? So we see if the object was intrinsically circular, let's say, for simplicity, then we would see it as slightly elliptical because of this lensing effect. Now, in the weak lensing regime, the beauty of it is that this distortion, when it's weak, is entirely described to first order by this distortion matrix that I showed before. Okay? So you can do a Taylor expansion of the distortion. If the distortion is weak, it's only the first term that matters, and it's this distortion matrix. And as we saw before, this distortion matrix, okay, so the distortion, how much this object is distorted, can be written is equal to an integral along the line of sight of the derivative of the gravitational potential times a weight function, and these weight functions are entirely known. You saw it was this ratio of distances and so on. So for a given cosmology, we can calculate it. If we know the redshift of the galaxy, we can calculate it exactly as a function of redshift. And so what we're really probing is the projection of the derivatives of the gravitational potential. So it means that since the gravitational potential is related to the density through the Poisson equation at late times, then it means that we can, using the distortion, by measuring this distortion, then we can basically probe directly or measure directly the projected density perturbation projected along the line of sight with this weight function. Okay. And as I said, this is important because this way we can measure the distribution of mass directly, which is what theory predicts best in the universe, as opposed to the distribution of light, and we don't have to assume a special relationship between light and mass, and we can directly map it. The advantage of the weak lensing is that since it only depends on the lowest order term, this mapping is one-to-one. Okay, so we can, from the distortion, we can directly make a map of the mass. Okay. Now, the question you're going to ask immediately is how do we measure this distortion? I'll tell you how. Okay, but let's assume we could measure the distortion from the shape of the observed shape of galaxies. Then we could make this inversion. Okay. Of course, the disadvantage also of weak lensing is that it's weak. So it's small, as I'll show you later. It's a small effect. It needs very careful measurement. It's much noisier, so you need a lot of galaxies. You need average of a large number of galaxies. But if you can do it, we have a one-to-one relationship. We don't have both the beauty and the complexity of strong lensing, which is nonlinear, which gives very strong distortions. Here the distortions are weak, and we can directly relate it to the mass. Okay. So again, in a little bit more detail. So the weak lensing is characterized by this distortion matrix that we looked at before. So it's a 2x2 matrix, which can be parameterized as a trace part. Well, it's an identity matrix plus a trace, which we call the convergence, and the trace-free part, which is characterized by this gamma 1 and gamma 2, which are the shears. Okay? And this distortion matrix, as I said, is equal to the projection of the gravitational potential derivatives along the line of sight, and the projection function is basically equal to the distribution of the redshift of the background galaxy that we're using. Okay, so we need to know the redshift of the galaxy that we're using for the lensing, which we can get from measuring the spectra of these galaxies or photometric redshifts, as I'll talk about later. So if you know the distribution of the galaxies that you're using, then you get the number of galaxies as a function of redshift or function of radius, and then you integrate this times this ratio of distances, always the same ratio of distances or combination of them that come about between the lens and the source of the lens, and so on. You integrate this and you get your weight function. In the past, we were considering one source, which had only one redshift, so this becomes a delta function. It collapses into just a ratio of distances. But in general, you can consider many galaxies that are lensed, and then what you need is integrate over the distribution of the redshift of the background galaxies. Okay, and as I said, in the weak lensing regime, we assume that kappa and gamma are very small, and it's all linear, and then you can invert the relationship. I'll show you how in a second. So how do we go from how do we reconstruct the mass? Well, let's go back to the distortion matrix, okay, with the two components, kappa and gamma. So I remind you, kappa corresponds to dilations and contraction of the images. So you take the intrinsic shape and you stretch it in all directions at the same time, or you contract. Okay, that will be parameterized by kappa. But if you stretch in one direction and contract in the other direction, then you distort it. You make the galaxy more elliptical, the image more elliptical, and that's characterized by this gamma, or the shear. And one can show, using some of the equations I showed you before, that kappa is equal to the projected mass density over this critical mass density, as we saw in the lensing equation, or in terms of the, you can define the lensing potential, which is a projected version of the gravitational potential, and then this kappa is basically the Laplacian of this lensing potential, while the gamma is our different derivatives of this lensing potential. Okay, so they're also second order derivatives, but different combination of the derivatives. So basically, what we can measure, as I'll show you how a little bit later, we can measure the shear by measuring the ellipticity of galaxies. And then from the shear, we can go back to kappa by reconstructing the potential and back to the kappa. And since kappa is the basically the projected mass density, we can reconstruct the mass. And as I said, in the linear regime, this relationship is one-to-one. Typically, one goes into the Fourier space and then back into real space to do this inversion. There are many techniques for doing it, but in the absence of noise, this is a one-to-one relationship. And in the weak lensing regime, this is a one-to-one relationship. Okay. And remember, the critical surface density is equal to this ratio of distances over this. Now, of course, if the galaxies that we use have a distribution redshift, then we need an average version of this. But don't need to get into the detail right now. So let me show you another kind of cartoon to illustrate how that works. Okay? All right, so let's consider the following. So let's suppose we have some background galaxies far away, and for simplicity in this kind of cartoon, we assume they all have the same flux and the same size. They're all circular for simplicity. We'll make that more complex later. Okay, so let's suppose that's how they would look like if we didn't have lensing. But let's suppose that between us and these galaxies, we have some mass distribution shown by this. So this would correspond in light blue to overdensities, and in black this would correspond to underdensities. Then the galaxies would get lensed by these mass density perturbations, and instead of seeing them like this, we would see a distorted version of them. Okay, I'm switching between the two, so they would be distorted. Here the effect has been enhanced by an enormous factor, so we can see it by eye. In practice, it's a very small effect. It has to be measured carefully statistically, as I'll explain a little bit later. But the idea is still illustrated by this. Okay? So what you see, for instance, is that you typically get a distortion of the galaxies which are stretched tangentially about overdensity. So if you look, for instance, at this one, this overdensity, you see that the galaxies tend to be stretched tangentially towards this overdensity. And you can show that analogously, the galaxies are stretched radially towards underdensities. Okay? And in general, you have complicated patterns of this stretching. Now, the one way to represent this distortion, and in particular the shear part of the distortion that makes the galaxies change the ellipticity of the galaxies, is to use a symbol for the shear. So what we do is we also show on the map of the density the shear as a line segment, okay, that you see here, which indicates the direction of the distortion, and the size of the line segment corresponds to the strength of the distortion. Okay, and so it's a way of representing that shear. So the shear has two components, gamma 1 and gamma 2. So it has basically two pieces of information which you can turn into a direction and an amplitude of the shear, and you can represent it by a line segment. So it's almost like a kind of like a vector field, okay, which has a value on the two-dimensional plane. But you notice that this vector has no arrow, right? It's just a segment, doesn't have an arrow, and that's because if you rotate by 180 degrees, the shear goes back to itself. Or another way to say this is that if you have an elliptical galaxies, if you rotate the elliptical galaxies by 180 degrees, you get the same shape. So that's why it's like some kind of arrowless vector field. Okay, and so you map it like this, and then the idea is to take, is to look at a small region of the image and look at the average shape of these galaxies, right? So in the absence of lensing, in this very simple case, they would be all circular, so the average ellipticity of the galaxies would be 0. They would all be circular on average. But if we have lensing, then they would all tend to be aligned in this direction because they all been stretched by the same lensing effect. So if we measure the average shape, and again I'll tell you exactly how one does this precisely. If you measure the average shape, then you can infer the shear. And so what you can do by looking at this in different regions in the image, you can map the shear. And then using the relationship between the shear and the conversion that I showed you before, then you can invert it and get a map of the kappa, or the density, which is shown in blue. So you measure the line segments, and then you do the mass inversion, and then you get to the blue map. If you look at a small region like this, okay, if there were no lensing, the galaxies would be, in this very simple case, they would be all circular, so they would not be on average elliptical. So if you look at the average ellipticity of the galaxy, it would be 0. Okay? Even if the galaxies had a small ellipticity, then they would be randomly oriented, and so they would average to 0. Now, because of lensing, they all stretch coherently in the same direction. So if you look at the average ellipticity of the galaxies in this pixel, then they would tend to all have an ellipticity in that direction. And that's caused by the shear. And as I'll show later, you can you can relate the ellipticity of galaxies to the shear. I'll show that in detail. But the idea is that we average over the ellipticity of galaxies in a pixel and find coherent alignment of galaxies, basically, if you wish. Right? Lensing is because it distorts all the galaxies together, the galaxies are all distorted by the same mass concentrations, then they all coherently align in some direction, which of course is different in different places of the sky. So by measuring the average ellipticity or the average shape of galaxies in a region, we can get a measure of the shear. But I'll give you, that step is actually crucial, so I'll show you later, I'll discuss how one does that quantitatively. But the idea is this. So the idea is that in the absence of lensing, the galaxies will be randomly oriented, okay? And with lensing, you create coherent alignment of the galaxies. Very small, but coherent. And you look for these coherent alignment. Another way to say this, you look for shape correlations. The shapes are locally, weakly correlated by the lensing, and that's what you look for. Again, I'll discuss that in more detail. Is that clear? Because that's the whole principle of it. So to finish, this is a more realistic simulation, which is done by Bhuvnesh Jain and collaborators. This is one of the first high-resolution map that was done. By now, this was done in 1997. There are much larger, more precise maps. But this is done by running an n-body simulation for the formation of structures and evolving it forward. And this is the kind of map that one gets. It's exactly the same convention I showed you before in this cartoon-like simulation. What you see in blue is the overdensity. So light blue correspond to overdensities, dark correspond to underdensities, projected along the line of sight. This is a region of the sky which is about 2 degrees by 2 degrees. Oh, sorry, it's half a degree by half a degree. Kind of the comparable to the size of the moon or some factor of the size of the moon. So it's a small region in the sky. So what you expect is patterns like this. So you see overdensities like this, with the shear shown as the line segment, which is tangentially oriented about overdensities, like this. And these overdensities are nothing other than clusters of galaxies which form in these simulations. You also see traces of filaments between clusters of galaxies, and the very small ones will be groups of galaxies. At this resolution, these are the only structures that is resolved. You also, if you go to very high resolution, you will see galaxies themselves and so on. Okay. So you see there's a kind of a complex patterns of the shear, which we can map and measure, we can characterize, and then compare to our models of structure formation and infer cosmology from it. Now the difficulty of it is that these weak lensing effect is weak indeed. So the kind of distortion that one expects, the amplitude of the shear we expect in random, in typical places in the universe are about a few percent. So it means that if you take a galaxy, its axis ratio gets affected by lensing by only a few percent. So the major and minor axes get changed by a few percent. So these are very small effects. You certainly cannot see it by eye. So you need to average over a very large number of galaxies to see it. And you also need to do measurements of shapes and the relationship between shapes and shear very carefully in order to measure it precisely. And that's part of the challenge, and where there's been an enormous amount of progress in the last 10 years or so. Okay. So what we'll do is we will next, I think if first Anjan is talking and me, I'll talk more about some of the things one can measure from this shear field from the theoretical point of view, how it relates to cosmology, and then later on, maybe today or tomorrow, we will discuss how we can actually do the measurement in practice. And after that, I'll tell you about the current observations of this effect and the cosmological constraints. But first, we need to have some tea, I think. Is it now? Tea. Okay. Any questions on this? Or? So one can typically measure the shear in 1 arc minute or so patches. So the resolution is about 1 arc minute or so. And the strong lensing effect that I discussed is really at the center. It would be if you have strong lensing on only the very more massive peaks, and it will be really at the center here. So in most of the sky, the strong lensing is negligible, and we're in a weak lensing regime. And as I said, it's very weak indeed.